Welcome back, GEOG 308. Today we're going to talk about physical geography, and I'm going to break it into two lectures, to make it a little bit smaller for you guys. So the first thing I want to do is have just a little geography quiz thing, and not a quiz, but a tidbit. And one is this question that's always kind of blows everyone's mind is, what's further west, Reno, Nevada, or Los Angeles, California? Now that's a trick question. You obviously know the answer because it's not Los Angeles. If you take a look at this map, you can see that Reno, as we come down, is actually further west than Los Angeles since the California coast bends down toward the east. Just a fun thing for you guys. So in physical geography, we're going to just do the basics. In each section, we're going to cover these in detail for each region, but we're going to talk today about physical landforms, climatic patterns, biogeography, and a bit on human impact on the environment, which will be the second lecture that we record. So the first thing to talk about with landforms is plate tectonics. And plate tectonics is a theory, but it's pretty much, I think, proven that the Earth is made up of different layers. We have the crust, we have the mantle, we have the core, etc., and that the surface is made up of different plates. You have oceanic plates mostly, which are underwater, obviously. And then we have continental plates that are above ground. And you can see the different ones here, the North American plate, the Caribbean plate, the Eurasian plate, etc., etc. Now, when you look at a map like this, if it looks like this one that I'm highlighting up here, up by Alaska, where it has triangles, that's a convergent plate where they're running into each other. If you have one that looks like a cross section here in the mid-Atlantic, that's a divergent plate that's pulling apart. And if you have one, a transform plate running next to each other, like the San Andreas Fault, for example, they're going next to each other. Now, here's kind of a cross section of the Earth. We have the core, of course, the mantle, and then we have the asthenosphere and the oceanic crust and the continental crust. So these are the different areas. And what you see are convection cells, where hot mantle is coming up from the core, and then as it goes up, it cools and turns around and comes back down. And it creates like a convection cell, if you will. And we have different ones that are running into each other, and that drives the plates that are above them. It makes them move one way or the other. So on this side, this one that I'm looking at here with my cursor, it's coming up and it's going this way. So it drives all the crust that way. On the other side, it drives it the opposite direction. On this one, they're running into each other. And we'll look at those different types of plate boundaries as we move along. So a divergent plate boundary is where they're pulling apart. Okay, they're pulling apart from each other. And down here in the bottom right shows kind of a diagram of how that works. And kind of a really important one is the Mid-Atlantic Ridge, where the Eurasian plate and African plate and the North American plate are pulling away from each other, as well as the South American plate. And so in the middle of this, we actually create new crust. So you have magma that's coming up, rising up from below, and it creates new land. It also creates lots of volcanoes, of course, and things where things can come out, such as Iceland, the Azores, etc. Now, a convergent plate boundary is when they're running into each other, and the oceanic crust is more dense than the continental crust, and so it gets subducted underneath. It gets pushed underneath. And what happens is that we create a trench as it's going down because it pulls them down. And then it creates fissures where water and magma come up, and that creates mountain chains with volcanoes. And honestly, that's my favorite plate boundary, which is odd that I have a favorite plate boundary. Here's an example of this down here in Central America and the Caribbean. So we have the Cocos plate that's running into the Caribbean plate, and it's making a subduction zone. And you have a line of volcanoes through Central America. And on the other side of the Caribbean plate, we also have the North American plate and the South American plate hitting the Caribbean plate from the other side. So the Caribbean plate's getting squeezed by both sides. We'll talk about that in more detail. So you have a chain of volcanic islands here, as well as along here. Here's an example of one of those. So again, here's that diagram that I had of the subduction zone. And looking at a map of Central America, you can see the trench as the Cocos Plate is coming up from the southwest, coming in and hitting the Caribbean plate, and it creates a trench. And all along this area right here, all these mountains are volcanic islands that have been created by that, and not islands, sorry, volcanoes. And they're active volcanoes at this moment. And you can see them when you go down to those areas. And we'll talk about that when we talk about the Central America. We also have only one that I can think of is a convergent plate boundary between continental plates. And they just kind of run into each other. The one that's more dense goes under, the one that's less dense gets pushed up, and it creates huge mountains. They just get uplifted. And we see this in places like the Himalayas. The Himalaya Mountains with Mount Everest, that's an example of this plate boundary running into it. It's the Indian plate running into the Eurasian plate, and that creates these huge mountains. No volcanoes because there's no water and it's they're running into each other. So no volcanoes, but a lot of earthquakes. And here's an example, just a map showing the running of the Indian plate into the Eurasian plate, and it creates the Himalayas and the Tibetan Plateau, thrusting them upwards in Mount Everest. And then transform plate boundary, which you guys should be familiar with since the San Andreas in California is on one of these, is where they're running side by side. And that generally creates lots of earthquakes, as you guys are aware. This is an example from the Caribbean where we have plate boundaries, and they're not just one plate, there's also faults lines all along it. And we see these, and we'll talk about this in more detail when we cover our regions, but it runs right through. And back in 2010, we had the huge earthquake in Port-au-Prince, Haiti, that killed almost 250,000 people, and it ran right through that capital city. So all of these are areas that you can see earthquakes happening. So here's the world plate boundary one. And again, like I said, if it has the pyramids, that's the way that they're being subducted. They're pushing in. So in South America, they're pushing in from the Nazca plate into the South American plate, creating the mountains of the Andes. And we see it also over here, and it's very complex when we get to, East Asia. And then what we can see on top of that, here are earthquakes and volcanoes. And I'll go back and forth, but you can see a relationship, I think, between the plate boundaries and this tectonic activity. The ring of fire over here is really crazy, obviously, with so many things going on with earthquakes and volcanoes, etc. And then that leads to basically geomorphology, the landforms that we see. Along those active boundaries, we see mountain building and new earth coming up and earthquakes, volcanoes, etc. But the places that are away from those boundaries are pretty much relatively stable. Over time, they've eroded. So the inland of the United States, we don't have a whole lot of activity, and so it's become much more plains. We see that in other places. In Australia, for example, does not have much tectonic activity. And so the areas that are away from plate boundaries are pretty much stable and they erode away. But the ones that are on the boundaries are actively creating new land and lots of new activity. All right, we're going to move now to climate. And this is very complex. We have whole classes on this, and so it's going to be very basic right now. And, talk to me if you have questions. So climate is the weather is what we see outside every day. So the weather today, it's extremely hot, but that's not the climate. Climate is the long-term patterns of temperature and precipitation across seasons. So you'll have areas where it gets hot in one season, cold in another. You have rainfall in one season, not in the other. And then how much rainfall and how much temperature you have, you add all that together and you create a climate. And so long-term patterns. So a couple of things that we're going to look at right now is solar energy and latitude, which we'll go into in a moment. Because all of our energy that comes basically comes from the sun. The Earth does produce some energy, but it's mostly from the sun. And latitude is our place on the Earth, north or south of the equator. Land and water interaction, we'll talk about that. Land heats and cools much more faster than water. And so water can minimize those changes. And so areas on the coastal areas tend to have much more temperate climates. Those that are inland have what we call continentality, meaning that they have much more extremes in temperatures. Then a much more complex thing is the global pressure systems and wind patterns. So as I'll talk about here coming up, basically air moves from high pressure to low pressure. And so that's where the winds come in. They go from high pressure to low pressure. And we'll talk about that coming up. And then precipitation. Again, much more coming up on that. So here's a basic kind of equation talking about the differences of incoming radiation from the sun. We call it insolation or incoming solar radiation. So that's why its insolation comes from. So all this energy is coming from the sun. Some of it, most of it actually hits the Earth's surface and it gets absorbed by the Earth's surface. And you can think about it like a black surface is really hot, that absorbs more. If it's a white surface, like in the polar regions, it reflects more. And that's what we see, that there's a bit that is reflected back out to space. And then some is reflected out by the atmosphere. Now, what the ground absorbs, it then re-emits it at a different wavelength. They call it infrared. That's heat. And that's what you can see on a black pavement. You can almost, sometimes on a hot day, you can almost see it coming up. And that's why you get that heat coming up. So that infrared radiation gets emitted back to space, but much of it gets absorbed by the atmosphere, by gases in the atmosphere, and then re-emitted back to the Earth's surface. Now, this basically balance keeps our world in a nice area where life can exist. And it goes up and down, as we'll talk about later in the class, global warming and global, dewarming that happens as well. But it's usually a balance. It equals out, but it goes up and down a little bit from, epoch to epoch. Now, another thing that's really important is understanding that the Earth is not like perpendicular to the sun. It actually is on an axis. It's 23.5 degrees off the axis, and it spins that way. And so when the sun hits directly on the Earth's surface, depending on the season, it's much more concentrated. There's less atmosphere to go through, and so you get a lot more heating. If you move up here, it's spread out more, so there's less. It's spread out more. And then if you get to the polars areas, it's spread out much, much more. It has to go through much more of the atmosphere, and it has the angle of incidence is not direct. Now, this is pretty simple. You guys probably know this, are different seasons. But let's come up here and start with our summer solstice. And that's a North American one because in South America, it's different. So the North American summer solstice is about June 21st. We just passed it. And that means the sun's energy is coming directly to the Tropic of Cancer. That's at 23.5 degrees north latitude. Okay. And that's where the sun rays hit direct. And that's where you get the direct energy and how it gets in that small circle that we saw in the last one. As we move into autumn, into the fall, we have the fall equinox. That's in September. And now the sun's rays are hitting directly at the equator. And at that time, every place on Earth has 12 hours of sunlight and nighttime exactly. But it's going directly at the equator. And so we see things cooling down at that time as we go into autumn. Then we move to the winter solstice for the northern hemisphere. And now the sun's rays are hitting directly at the Tropic of Capricorn. And that's 23.5 degrees south latitude. So that's the summer in the southern hemisphere. But it's our winter, of course. And so the sun rays that are hitting us is oblique, and we don't get as much, and it's spread over more areas. And then we come into the spring equinox, springtime. Again, the sun now is hitting directly at the equator, and we get 12 hours of sunlight all around the world. and things start warming up a bit for us, and then it returns. Now, land and water interaction is also important with this. Water is basically the conveyor belt of energy around the world. So we have between the tropics, and that's what the tropics are called, between the Tropic of Cancer and the Tropic of Capricorn and the equator, that's where sun hits directly at some point in the year. And so a lot of energy builds up there, and you think it just gets super hot. But water moderates that. It absorbs a lot of that energy and then it moves it. And so, and it goes in this type of a cycle all around the world. So it gets warmed up at the equator. It comes up toward the eastern coast and it's warm water. So the Gulf Stream across the east coast of the US is warm. And that actually goes up into Europe, allowing Europe, which should be much colder than it is, but because of that warm water, it moderates the temperatures and makes it better. But then as it comes back down, it cools and then it picks up heat, and then it goes up and just makes a circle. We can see that here in the Gulf Stream here in by North America, but in the South, in South America, it's the reverse. It comes and it goes south. And so the warm water is going south along that eastern coast of South America. Oops. And then comes up and it gets cold water coming from the Antarctic. And then it's a cold current coming up the western section of Africa, but it warms up at the equator and comes back. And I'm not going to keep doing that, but it keeps happening. So for California, and this map doesn't work well, if we start with the north equatorial current, it comes up by Japan. It's a warm current. And then it cools down and it comes across through the North Pacific and comes down by California where it becomes very cold. And then it goes by the equator and it goes back around, basically a convection cell. I remember the first time I came here, I did my work in the Caribbean and the water there is like 80 degrees year round. And I was like, oh, I came to California, went jumping in the ocean. And I was like, this is really cold water. And I was like, okay, I understand why. It's because the West Coast get cold currents, the East Coast get warm currents. And that's a good thing to kind of keep in mind. And this just shows this idea right here that water takes 5 times longer to heat than land. So land heats and cools much quicker than the water. And so if you're close to the water, it moderates your temperature. So you can think about here and like if you go to Morro Bay today, I'd like to go there today. It's probably like 65, 70 degrees. And up here, it's going to be over 100 degrees. And I'm inland where I live up at by, I'm saying North County. And an example of this, as a kid, I'm from New Mexico, but as a kid, I grew up in North Dakota. And North Dakota is the geographical center of North America. It's the place that's the furthest away from any water body. And in the summer, it'll get 110 degrees. In the winter, it'll get 40 degrees below zero. Extremes because the land heats and cools much quicker. But Seattle, which is at the same latitude, close to the ocean, it kind of varies between 80 and 60 degrees. So the water really moderates those temperatures. So along coastlines and places with major water bodies, you want to think about that. That moderates the temperatures. But if you go inland, and even here in San Luis Obispo area, it really varies. In 8 miles, you can go from 70 degrees to 110 this summer. Hope that doesn't last too much. All right. Probably the most complex thing talking about climate is wind patterns. Okay. And I have a thing coming up. And if you get a chance, jump on, I'll put these slides onto Canvas and you can actually watch the video with their narration. I can't get it while I'm doing this on Zoom. I'm going to try to talk about it in the next one. But basically, low pressure means that air is rising. And that happens like hot air. Think a hot air balloon, that's low pressure. It rises. High pressure goes down. Okay? So around the equator in the tropics, you have a lot of heat coming in, and that heats up the air. It gets a lot of moisture out of the atmosphere or out of the oceans, and it rises. And so right here, we have the intertropical convergence zone. It's an area of, of low pressure. So when you get here, the air is rising and it creates, and as it rises, it cools down, and hot air can hold more moisture than cold air. So as it rises, it cools down as it goes up in the atmosphere, and then it can't hold as much moisture, and then it starts raining. So we have the greatest amounts of precipitation along this area, along the equator, give or take 8 degrees north or south. But the air has to go somewhere once it goes up. So it moves north in the northern hemisphere and south in the southern hemisphere. It's lost moisture, and then it starts to warm up, and then it descends. It comes down. And that's what the high areas are, is descending warm air. And it has not much moisture. So these are the areas that are dry. That's where our great deserts are. Okay, we can think like the Southwest, Baja, you know, other deserts that we have, Namibian desert, Australia is very dry because that air comes down. And as it comes down, it has to go somewhere. It gets like a pressure pushing down. So some of the air gets pushed back to the equator where it picks up moisture. It's warm and it picks up moisture and it becomes the northeast trades. And in the southern hemisphere, the southeast trade winds, and they come back toward the equator. Other air is pushed to the north or the south, and that creates the westerlies. So you can see the Hawaiian high over here. Some air is being pushed toward the westerlies, and some is being pushed toward the northeast trade winds. And so if you think about storms that come to California, but much more important, like in Washington State, everything comes off the Pacific. And that's because of the Hawaiian high, low, high pressure system pushing that air that way, picking up moisture and comes in and creates the storms that come that way. And that happens all across the world. So again, the idea is the northeast trade winds, basically from the tropics down, they come from the northeast, and that's the direction of the wind. It's coming from the northeast. And in the south, it's the southeast trade winds. And they converge at the tropical, intertropical convergence zone, the low pressure system, and they rise up, drop off the rain, and they move back to the high pressure systems. And that creates those. So I know it's a very complex thing. We can talk about it more. It's easier in class where we can actually diagram it and answer questions. But that's something that you should look at. And I would like to have you guys, if you have a chance, to watch this video. You won't be able to hear the audio, but I'll try to talk about it. But this is on the PowerPoints that I put on Canvas, and this explains it very well. So intense heating of the equator. So it rises up, creates precipitation, and it rises to the poles on either side, and then it sinks when it's warm, about 30 degrees north and south latitude. And that's why they have high rainfall at the equator, because it can't hold the moisture when it rises up and cools down. We call these Hadley cells. But at 30 degrees north, when they're coming down, they have less moisture and they're warmer, and that's where our major deserts are. And the Coriolis effect, because the Earth spins, means that instead of going directly down, they move. So we have northeast trade winds. They get moved by the Coriolis, because of the Coriolis effect and the spinning of the Earth. So we have southeast trade winds and northeast trade winds. So you go right of their path in the northern equator and to the left on the southern equator. So we'll stop there and move on. Sorry, I just kind of screwed that up. I'm trying to get this out. Just stop. So one thing people always say is if you look at toilets and how they flush in the northern hemisphere, they go to the right. The southern hemisphere, they go to the left. That's not true. It's the design of actually the toilet. So just to throw that out there. All right. A second thing, hopefully that makes sense. Watch it again, if you can, on Canvas, where you can actually watch it and the person demonstrates and talks about it. But basically, near in the tropics, things come from the east. In out of the tropics, they mostly come from the west in terms of wind patterns and storms and whatnot. Now, orographic precipitation, orographic basically just means mountain processes. And what we have is the orographic effect means that air comes in on the windward side where the wind's coming. So here in California, it's coming from the Pacific, right? Other places are coming from the east. So here's coming from the west. In the tropics, it comes from the east. And as it comes, you have moisture. And basically, as you move up in elevation, it cools. And cold air cannot hold as much moisture as warm air. So you have a warm air pocket with a lot of moisture. And as it moves up, it gets colder, about 4 degrees Fahrenheit every 1,000 feet you go. And so the windward side, as it goes up, it cools down, and that creates precipitation. Eventually, it cools down where it can't hold that moisture anymore. And so the windward side is going to be very wet. You can see that in the Sierra Nevadas, right? As you go to the Sierra Nevadas, like by Yosemite, you get these pine forests, you get much more moisture. But if you drop over, the air has lost some of its moisture. It's also warms as it goes down, and that's called the leeward side or the rain shadow. So if we think of the Sierra Nevadas, as you go up through, Kings Canyon, whatever it is, Sequoia, you have a good amount of moisture. But as you drop down, you go to Death Valley, which is dry as a bone. You see that in Oregon, you see that in a lot of places, and that's something that we'll see all around the world. So in North America, we see it coming from the west, coming up, and that's much more moisture. As you drop down, you get that rain shadow effect on the backside of the mountains. In the Caribbean, as we'll talk about, it's actually the winds are coming from the east, the northeast. So that side gets the rainfall, and the southwest side gets less rainfall and becomes a rain shadow. So looking at global precipitation patterns, you can see along the equator, we have these kind of nice green or aqua colors. That's high rainfall. That's along the equator, you know, intertropical convergence zone where the winds are coming together and rising. So you have a lot of moisture. And then you'll see where the winds are coming into different directions. You'll see high precipitation because of the orographic effect. In North America, we can see it. You see greens along the coast, and then you get drier as you get inland. And that creates climates. And the basic way to look at climates and take a look at this so that we understand that throughout the course, and we'll do it for each class, is that we have wet climates, A, dry climates, which are B, mild mid-latitude climates, which are C, D are temperate mid-latitude climates, polar climates, and highland. We're not really dealing with polar climates or highland in our class, and not much on the D climates, a little bit. So we're going to be focusing on the first three, A, B, and C within our class, or in our class. So we don't have to worry too much about these D, E, and F climates. A, B, and C are the ones that we'll be dealing with mostly. So with wet climates, we have tropical rainy and tropical monsoon. Think about tropical rainforests, extremely wet, and that AF and AM are in these reds. And you can see that's mostly along the equator, with a few exceptions based on wind patterns, water patterns, and topography, but they're very much in the tropics. Then the tropical wet and dry savanna, which is in this kind of pink color, are on either side. As you go either side of the equator, because of the seasons. they become seasonal. So one season they'll be wet, next season they'll be dry. And that's on either side. You can see it pretty much fits a pretty good pattern. And Africa is pretty much the best way to look at all these climates because right in the middle, you have that tropical wet climates. When you get to Western Africa or Eastern Africa, I'm sorry, you have some highlands and mountains, and that alters things. The dry climates are steppe, which is like kind of scrub grasses and things like that, and then desert and grasslands. And you can see that in Africa. So on the north side, you have the savanna climates, and then you go to the steppe climates, and then you go to desert. And this is how things would be if the world was completely equal. But it's not because we have different shapes of continents, different oceans, etc. So it's the basic idea, if you can get that. And then mild mid-latitude climates happen after that. So we have things like Mediterranean climates, like here in California or the Mediterranean. And we also have marine West Coast climates, like we see in Oregon and Washington State. And humid subtropical, which is CA. We're not going to deal with too many of those. The main ones would be down here in South America and in that's pretty much the only ones maybe in Australia a bit. And that's like if you think about the southeast of the United States, like Atlanta, Georgia. Just think about the climate there. That's kind of the way that I do it. So A, B, and C, and then these sub ones are what we're going to be focusing on mostly in our class. All right, I'm going to stop sharing at the moment and we'll start again with our next lecture.